Hello, good day everyone. So here's an example of adding vectors. It is similar to the last example I gave to you in the classroom setting. That was my video recorded in the NASA classroom. But now this example has corresponding magnitude given to the variables. So for example, we have here two vectors having magnitudes and directions or angles plotted on a Cartesian plane. So we have vector A having magnitude 53 meters on the direction northeast 20 degrees, and vector B 34 meters still northeast having a direction of 63 degrees. So we are to find the magnitude and direction of the resultant vector. What is a resultant vector? It is the vector sum of the two vectors here, which is also, we can say that it is the shortest distance from the starting point, which is from the origin to the here, from here to the end point here. So we can say that's our resultant vector. We are to find its magnitude and its direction, or theta r. So before we can find the magnitude and direction of the resultant vector, it is very necessary for us to first find the components of these two given vectors A and B. So here's for our solution. Components of vector A along the x and y axis. How to do so? We have given the magnitude of the vector A and its angle or direction 20 degrees. So for the component of vector A along the x-axis, we can use this equation. Ax is equal to A cosine theta. Where did it come from? If you still can remember our discussion regarding the right triangle, if our hypotenuse or the C, the longest side of the right triangle, is A, the component of that A along the x-axis or along the horizontal is AX, and the opposite or the component of A along the y-axis is AY. So we can say that that's a right triangle because of the two perpendicular sides, this and that, which forms a right triangle and 90 degrees. So this is adjacent side of the right triangle, the opposite, and the hypotenuse. And finding each side of this triangle, we can make use of the trigonometric functions. And it is very known for you also that we can use SOHCAHTOA. If you still can remember SOHCAHTOA in your trigonometry, SO is sine is equal to opposite over hypotenuse, Ka cosine, adjacent over hypotenuse, TOA tangent, opposite over adjacent. But in this case, since we are to find the component of A along the x-axis or the adjacent side or the AX, we can make use of Ka, cosine adjacent over hypotenuse, because hypotenuse A is equal to 53 meters. And cosine, we can make use of this angle. So the only thing here is unknown, which is unknown, is A, or the AX. So how come that from cosine is equal to adjacent over hypotenuse, we have this formula because of this. So cosine theta ka is equal to AX adjacent over hypotenuse A. From this expression, we can multiply both sides of the equation by A so that A here can be eliminated, leaving this expression alone, which is the unknown. A cosine theta is equal to AX over A, multiplying both sides by A, these two A's here, and A. Now, this can be eliminated. Now what will happen? This becomes A cosine theta is equal to AX, because these two A's are already eliminated, which is this final equation, same with that one. AX is equal to A cosine theta. Now, using this equation, let's put the values. A is equal to 53 meters, cosine, copy the function, and the angle 20 degrees. Our AX, or the component of the vector A along the x-axis, is now 49.8 meters. So the same with the component along the y-axis, but in this case we have to use SO, or sine opposite over hypotenuse. So just like how we do these expressions here, to solve for AY, we have to do the same. AY is equal to A sine theta. This is our goal here is to remain the unknown variable on the other side of the equation so that we can solve for it. So A sine theta, where A is 53 meters, times sine, angle is 20 degrees, which is equal to 18.1 meters. You can actually calculate it to check if it's correct, if my calculation is correct. Thank you very much. Okay, for letter B, components, our next step. Since we got already components of vector A, now we will get the components of vector B along the x and y axis. This is a step by step. Okay, so given we have the magnitude of B, vector B, which is 34 meters, and its angle or direction 63 degrees. So the same process with how we got the components of vector A along the x and y axis. Just always remember, if the component along the x-axis is unknown, you have to use cosine. If the component along the y-axis is unknown, you have to use sine. So do the same. You put the values. B, for the magnitude of B, 34 meters. The angle is 63 degrees. So 34 meters cosine 63 is equal to 15.4 meters. For the component along the y-axis, you always use sine. To avoid confusion, we have to be consistent. That if x is a known, we have to use cosine function. If y is a known, we have to use sine function. For B, we have 34 meters, that's the magnitude, and sine angle is 63 degrees. So 34 meters times sine 63 degrees is 30.3 meters. That's the magnitude of the component of vector B along the y-axis. Now that the components are all unknown, we can solve for the magnitude of the resultant vector. How? Okay, components of the resultant vector. If you still can remember, this figure shows here. So this one's our vector A and vector B, and we have determined that this is our resultant vector. So how to find its components along the x and y axis? If you're going to extend the line here and here, we can make a figure, a right triangle, in which this side up to here is the component of A along the x-axis, which is AX. And this one, if you're going to extend it here, you're also making a right triangle in which this side is the component of B along the x-axis, which is BX. So it's very clear that if you're going to add these two, AX and BX, that makes the component of the resultant vector along the x-axis, which is the R sub x. So Rx is equal to AX plus BX. Also with the y along the y-axis, the component of R is this side is clearly AY, or the component of the vector A along the y-axis, and this side is also, this one is by, which is the component of the vector B along the y-axis. So if we're going to add these two, this whole side of this triangle makes the y component of the resultant vector. So ry is equal to ay plus by. So since all of the components of these vectors A and B are known, we can solve for the components of the resultant vector along the x and y axis. It's very necessary for us to know first these sides of the resultant vector, or these components of the resultant vector, to find its magnitude, because it's very hard to solve for its magnitude when nothing is known yet. Okay, so here we have AX is equal to 14.8 meters, BX 15.4 meters, AY is 18.1 meters, and BY is equal to 30.3 meters. RX is equal to AX plus BX, all X. It is very impossible that you're looking for the resultant vector along the x-axis, and the other known variable here you're going to use is along the y-axis. So that will be impossible. So it must all be along the x-axis. Let's see, AX is 49.8 meters plus 15.4 meters for BX. RX is equal to 65.2 meters. The same process, RY is equal to AY plus BY. So the answer is 48.4 meters. Now that we have the components of the resultant vector along the x and y axis, we can now solve for the magnitude using, when it comes to right triangles, finding the sides of a right triangle, what formula is very powerful when it comes to right triangles? If you still can remember, it was formulated by Pythagoras. It is the well-known Pythagorean theorem. C squared is equal to A squared plus B squared, where C is the hypotenuse, A can be the adjacent side, B is the opposite. So C is the hypotenuse, that means our R is the C side of the right triangle. So we can make use of this. R is equal to square root, because eliminating the square of the other side of the equation would mean that you have to both introduce a square root of on each side. So it was eliminated here on the other in this side of the equation. The square was eliminated because of this square root, leaving the other side of the equation has square root. Okay, so r is equal to square root of rx squared plus ry squared. So Rx is 65.2 squared plus 48.4 squared. Square root, the answer is 81.2 meters. So that's the magnitude of our resultant vector. Are we done? Not yet, because we still have to find its direction. How to find direction? Using the functions or the trigonometric functions, we can make use of the tangent function. So katawa, so I can make use of the tangent. Tangent theta is equal to ry over rx. Since we already have known these two components of the resultant vector, we can now solve for its angle. But using this one, why would we have a negative 1 here? That's what we call inverse tangent. So that the remaining variable here on the other side is the angle, because we're looking for the angle. Okay, so tangent or inverse tangent times, put the values, ry is 48.4 divided by rx 65.2. If you're going to calculate that, the answer is 36.6 degrees. Okay, so I hope you understand how we solved it. You can actually replay it if there's unclear explanation, or ask me through my social media accounts. So here's the final answer. Our resultant vector is 81.2 meters, having direction of 36.6 degrees. Thank you so much for listening. Got a question in your mind? Just log on to your Schoology account, comment on the discussion section intended for your clarifications. Thank you.